A tooth that survived 30 million loading cycles breaks on a piece of bread. Soft bread. The same bread you ate yesterday. The tooth was weakened by the 30 million cycles that preceded the bread, each one loading the hardest substance the body produces below its failure threshold, each one propagating microcracks through the crystal by a distance too small to measure on any single cycle. The accumulated damage reaching failure length at the moment the bread applied the final load. You felt nothing during the accumulation. No warning. No progressive loosening. No gradual weakening you could have detected. The fatigue network grew silently because each crack increment was smaller than any sensation the tooth's nerve could register, and the crystal's structural capacity remained adequate for every load until the final one. The failure appeared instantaneous from the outside. The failure was 30 years in the making from the inside. The bread was the last cycle. The fracture was the history. Enamel is 96% mineral by weight, the highest mineral content of any tissue in the body, composed of hydroxyapatite crystals packed in parallel rods running perpendicular to the tooth surface. Harder than steel, more brittle than glass. Laid down once during tooth formation by cells called ameloblasts that die after the enamel is complete and are never replaced. The enamel on your teeth at 60 is the same enamel that formed before the tooth erupted in childhood. Every crack, every acid exposure, every thermal cycle it has absorbed since then is written into the crystal as accumulated damage that no biological process can erase. The tooth at 60 carries the complete mechanical and chemical history of every meal, every drink, every temperature change, and every grinding episode across 6 decades, all recorded in a material that was laid down once and has been absorbing insults ever since without any cellular mechanism to read the damage report or initiate repairs. No cell maintains it. No cell can rebuild it if it cracks. The crystal structure is the structure you received, minus whatever decades of chewing, thermal cycling, and chemical dissolution have removed. No other tissue in the body operates this way. Bone remodels continuously through osteoclast and osteoblast activity. Skin replaces its surface every 2 to 3 weeks. The lens crystallines are the closest parallel, laid down once and never replaced, but the lens sits in a protected, fluid-filled chamber. The enamel sits in the mouth, the most mechanically, thermally, and chemically hostile environment in the body, absorbing every force, every temperature change, and every acid the diet delivers, without any cellular maintenance between insults. How does a material harder than steel crack from chewing bread? Fatigue fracture. An engineering failure mode that operates on any material loaded cyclically below its fracture threshold. A single chewing cycle generates approximately 70 megapascals of stress on the enamel surface, well below the ultimate fracture strength of approximately 380 megapascals. Any single bite is safe by a factor of 5. The margin is enormous on any single cycle. But you chew approximately 1,000 to 2,000 cycles per meal, 3 meals per day, 365 days per year, for 40 years of adult eating. If you grind your teeth during sleep, the overnight cycles add thousands of additional loads per night at stress levels that may exceed normal chewing because the grinding forces are unregulated by the feedback mechanisms that limit conscious biting. Bruxism accelerates the fatigue timeline by adding loading cycles during the hours the teeth would otherwise rest. The total approaches 30 million loading cycles by age 55. Each cycle individually safe. Each cycle adding its increment to a network that grew invisibly across 3 decades of otherwise normal eating. 30 million applications of 70 megapascals, each one individually safe, each one propagating the crack network by an increment too small to detect on any single bite. But each cycle propagates existing microcracks by a small increment through the crystal, a growth rate described by Paris law. The crack advances per cycle as a function of the stress intensity at the crack tip, raised to a material-dependent exponent. The crack tip is the point of maximum stress concentration in the crystal. The narrower the crack, the more the applied stress concentrates at its leading edge, the faster the crack grows. As the crack lengthens, the stress intensity at the tip increases by the square root of the crack length. A crack twice as long concentrates stress approximately 1.4 times more intensely at its leading edge. The relationship means crack growth is self-accelerating. Longer cracks grow faster because they concentrate more stress, and faster growth makes them longer, which concentrates more stress still. The first 20 million cycles may propagate the network by a fraction of a millimeter. The last million cycles may drive it through the remaining crystal in weeks. The acceleration is why the tooth seems to break suddenly. After decades of apparently identical loading, the crack was growing slowly for years, then rapidly in the final months, then catastrophically on the final cycle. An aircraft wing experiences the same physics. Each flight loads the aluminium alloy below its failure threshold. Any single flight is safe, but the accumulated cycles propagate fatigue cracks through the metal, and the wing has a certified fatigue life, a maximum number of cycles after which it must be inspected or replaced because the crack network has reached a length that risks catastrophic failure. The enamel on your teeth has no inspection schedule, no replacement option, and no living cells maintaining the structure between cycles. The aircraft wing has mechanics, inspections, and the option of replacement when the fatigue life is reached. The enamel has none of these. The crystal absorbs every cycle without repair, without maintenance, and without any mechanism to reverse the crack propagation that each cycle adds. The fatigue life is whatever the crystal can sustain across a lifetime of chewing, and the bread at 57 was the cycle that exceeded it. The food was irrelevant. The patient who tells the dentist it broke on bread is describing the trigger, not the cause. The cause was the fatigue network that had been propagating for decades. The bread was the delivery mechanism for the final chewing load. Any food, any bite, any mechanical load at any point during that day would have completed the same fracture because the crack network had already reached the length at which any normal chewing load exceeds the remaining crystal's resistance. Hard food, soft food, the specific material on the tooth at the moment of failure is incidental. What matters is whether the fatigue network has reached the length at which the next cycle, any cycle, completes the fracture. A tooth that would have broken on bread would have broken on anything else that applied the same chewing load. The failure was waiting for any load. Crack propagation in dental enamel follows Paris law through measurable growth increments. Enamel exhibits classic fatigue behavior with crack growth accelerating as the network lengthens and stress concentration at each tip intensifies. Arola and colleagues measured these rates in the Journal of Dental Research. The disc herniation discussion described identical physics in a different material, decades of spinal flexion cycles propagating microtears through the annular collagen fibers of the intervertebral disc, each tear too small to feel, the accumulated damage breaching the wall when an ordinary lift exceeded the remaining structural margin. Different material, different anatomy, same Paris law. The disc bore millions of spinal loading cycles. The tooth bore millions of chewing cycles. Both reached their fatigue limit in the same decade because both accumulated damage at rates proportional to their loading frequency across the same duration of adult life. I traced the crack in my own molar to the fatigue arithmetic the week the engineering replaced the word brittle in my understanding of why the tooth broke. The bread applied the chewing load to a crystal that could withstand 380. The bread was safe. The 30 years of chewing that preceded it had propagated the fatigue network to a length where the chewing load was sufficient to complete the fracture the history had been building. The tooth was not brittle. The tooth was fatigued. Crack propagation through the crystal accumulated across decades of mechanical loading. But the cracks do not start randomly across the enamel surface. They start preferentially at one specific location, the interface where two materials with different physical properties meet, and the physics of why they start there runs through the coffee you drink every morning. Where did the crack start, and why does temperature matter? Dentino-enamel junction, the boundary where the enamel meets the underlying dentin. Two materials bonded together with different thermal expansion coefficients. Enamel expands and contracts at approximately 11.4 times 10 to the minus 6 per degree Celsius, dentin at approximately 8.3. When you drink hot coffee, both materials expand, but the enamel expands faster than the dentin it is bonded to. The mismatch creates shear stress at the interface, the same stress that causes tile to crack when the concrete beneath it expands at a different rate. When you follow the hot coffee with cold water, both materials contract, but again at different rates, generating shear stress in the opposite direction. Each thermal swing produces a cycle of interfacial shear that adds to the fatigue loading the chewing produces. Cracks nucleate preferentially at the dentino-enamel junction because that is where the shear stress concentrates. Thermal cycling alone does not crack the enamel. It initiates microcracks at the interface that the mechanical chewing cycles then propagate through the crystal. Two fatigue inputs, mechanical and thermal, converging at the same structural weak point, each contributing its increment per cycle to the same crack network. The tooth that cracks at 57 lived through approximately the accumulated cycles, mechanical cycles, and 30,000 thermal cycles, both inputs accumulating at the dentino-enamel junction where the expansion mismatch concentrates the shear. The junction is the structural weak point because it is the only location in the tooth where two materials with different physical properties are permanently bonded, and every thermal swing tests that bond. Now the hot coffee followed by the ice water, the hot soup followed by the cold drink, each temperature swing adding shear stress at the junction where the two materials meet. The morning routine of hot coffee followed by cold water concentrates two thermal cycles within minutes, loading the dentino-enamel junction with back-to-back shear reversals that the 33,000 cycle estimate may undercount for habitual hot, then cold drinkers. The number of significant thermal cycles per day depends on your eating and drinking pattern. 3 hot to cold transitions per day across 30 years is approximately 33,000 thermal cycles, added to the accumulated cycles, mechanical cycles, each one loading the same interface where the cracks preferentially form. Fatigue cracked the structure. Thermal cycling initiated the cracks at the weakest interface, but the crystal surface was under a second attack the entire time, a chemical dissolution that runs after every meal, invisible, reversible, balanced by a repair fluid the body produces continuously, until the repair fluid was reduced by the medications you started taking at 55. What happens to the enamel surface after every meal? Stephan curve. Streptococcus mutans, the primary acid-producing bacterium in dental plaque, cleaves sucrose into glucose and fructose using an enzyme called glucosyltransferase. The glucose enters glycolysis, the same metabolic pathway every cell in the body uses, but under the anaerobic conditions beneath the plaque biofilm, the endpoint is lactic acid rather than the carbon dioxide and water aerobic metabolism produces. The lactic acid accumulates at the tooth surface because the biofilm traps it against the enamel. Stephan documented this in the Journal of the American Dental Association in 1944. Within 5 minutes of sugar reaching the plaque, the pH at the tooth surface drops from the neutral 7.0 to approximately 4.5. The dissolution threshold pH for enamel dissolution is 5.5. Below 5.5, the hydroxyapatite crystal dissolves. Calcium and phosphate ions leave the crystal lattice and enter the surrounding fluid. The enamel surface dissolves at the atomic level after every meal that contains fermentable carbohydrate. Saliva reverses the dissolution. Saliva is a supersaturated solution of calcium and phosphate ions, carrying higher concentrations of both minerals than the fluid surrounding the tooth. Salivary buffers, primarily bicarbonate, neutralize the bacterial acid. The pH climbs back above the dissolution threshold within 20 to 40 minutes. Above the dissolution threshold pH, the supersaturated saliva deposits calcium and phosphate back onto the crystal surface. Remineralization. The atoms return to the lattice. The surface rebuilds. Balance between dissolution time and remineralization time determines whether the tooth gains or loses mineral across each day. 3 meals per day produce 3 Stephan curves, 60 to 120 minutes of total dissolution time, with the remaining 22 to 23 hours above the dissolution threshold, during which the supersaturated saliva deposits calcium and phosphate back onto the lattice, atom by atom, rebuilding what the acid removed. Across a full day, the remineralization time exceeds the dissolution time by a ratio of approximately 12 to 1. The balance favors remineralization by a wide margin, and the tooth maintains its mineral content because the repair runs for far longer than the damage. Constant snacking changes the arithmetic. 8 to 10 eating events per day produce 8 to 10 Stephan curves, 160 to 400 minutes of dissolution time. The remineralization windows between eating events shrink, because each new sugar exposure resets the pH to 4.5 before the previous curve has fully recovered. The balance shifts toward net dissolution. The enamel surface loses mineral across each day by an amount proportional to the number of Stephan curves the eating pattern produces. Eating frequency determines another cycle count beyond the gut, the Stephan curve. More meals mean more dissolution time. Fewer meals with longer gaps mean more remineralization time. The same frequency physics applied to the tooth surface that the meals discussion applied to the gut surface. Fork frequency is upstream of enamel dissolution through the number of acid cycles the plaque produces per day. Well, the Stephan curve arithmetic landed differently once I mapped the snacking through dissolution time rather than calories. Each mid-morning granola bar was 20 to 40 minutes of dissolution time added to the daily total. A Stephan curve the enamel surface had to absorb without a corresponding extension of the remineralization window. The sugar content mattered less than the frequency. 3 squares with no snacking. 3 curves, manageable dissolution. The same total sugar distributed across 6 eating events. 6 curves, double the dissolution time, half the recovery time. A typical grazing day mapped against the Stephan curve: breakfast at 7, coffee with sugar at 9:30, snack at 11, lunch at 12:30, afternoon snack at 3, dinner at 6:30, evening dessert at 8. 7 acid exposures, 140 to 280 minutes of dissolution time, less than 4 hours of recovery between the last evening exposure and sleep. The frequency was the variable, and the frequency was set by the eating pattern. Stephan curve runs after every meal. The remineralization runs between meals. The balance held for decades because saliva provided the minerals and the buffers the repair required. One modification to the crystal structure shifts the balance permanently in favor of the enamel. How does fluoride change the crystal? Fluoride ions substitute for hydroxyl groups in the hydroxyapatite lattice, converting hydroxyapatite to fluorapatite. 1 ion swapped in each unit cell of the crystal. The substitution drops the critical pH from 5.5 to approximately 4.5. The same bacterial acid that dissolved the original crystal at the dissolution threshold cannot dissolve the fluoride-modified crystal until the pH drops a full unit lower. The acid still forms, the pH still drops, but the crystal resists dissolution across a wider pH range because the fluoride-modified lattice is thermodynamically more stable than the original. The practical significance is measurable. A tooth surface with fluorapatite in its outer layer can withstand the Stephan curve from a normal meal without significant mineral loss because the pH rarely drops below 4.5 even at the curve's nadir. The same meal on unmodified hydroxyapatite produces measurable dissolution because the nadir of 4.5 to 5.0 sits below the original crystal's threshold of 5.5, but above the fluorapatite threshold of 4.5. Fluoride toothpaste delivers fluoride ions to the enamel surface during brushing. During the next remineralization cycle, when the salivary calcium and phosphate deposit back onto the crystal, the available fluoride ions incorporate into the regrowing lattice. The repaired surface contains fluorapatite, which is more acid-resistant than the original hydroxyapatite it replaced. Each remineralization cycle that incorporates fluoride produces a surface that is incrementally more resistant to the next dissolution cycle. The toothpaste is engineering the crystal at the atomic level, 1 ion substitution at a time, rebuilding the surface with a more durable material than the original. The practical implication: fluoride toothpaste is most effective when used twice daily because each application provides the fluoride ions that the next remineralization cycle incorporates into the crystal. Skipping the evening brushing eliminates the fluoride delivery that would have been incorporated during the overnight remineralization window, the longest uninterrupted repair period of the day. Fluoride incorporation into the crystal lattice produces measurable increases in acid resistance at the enamel surface. Featherstone established this equilibrium in the Journal of the American Dental Association, and then the repair system that maintains the balance depends on saliva. The fluoride strengthens the crystal. The calcium and phosphate rebuild it. The bicarbonate buffers the acid. Every component of the repair runs through saliva. When the saliva stops flowing, only the dissolution side of the equation continues. Xerostomia, dry mouth from medications. Antihistamines, antidepressants, antihypertensives, and the thiazide diuretics that have appeared across multiple body systems as sodium depleters, potassium depleters, photosensitizers, orthostatic destabilizers, urinary frequency amplifiers, and now salivary suppressors. The 7th consequence of one prescription class. Medication reduces salivary flow rate by blocking the muscarinic receptors on the salivary gland cells that trigger secretion, or by reducing the fluid volume available for secretion through the diuretic effect. Thiazides operate through the second mechanism. By increasing renal water excretion, the total body fluid decreases, and the salivary glands produce less fluid from a reduced supply. The dry mouth you experience as a side effect is the salivary glands attempting to secrete from a body that has less fluid to spare. Less saliva means less buffer to neutralize the bacterial acid. The Stephan curve drops deeper and recovers slower. Less saliva means less supersaturated mineral solution to deposit back onto the crystal. The remineralization that maintained the balance for 4 decades weakens. The dissolution runs unopposed. The nighttime hours are the most vulnerable. Salivary flow rate drops naturally during sleep to approximately 10% of the daytime rate. If medication has already reduced the daytime rate, the overnight rate may approach 0. 8 hours of near-zero salivary flow means 8 hours without buffering, without mineral deposition, without the washing action that clears bacterial acid from the tooth surface. The bacteria that produce the acid are still metabolizing the residual sugars from the evening meal. The acid they produce accumulates on the tooth surface without the salivary dilution that would normally wash it away. The overnight dissolution runs deeper and longer than any single daytime Stephan curve. The overnight Stephan curve from the evening meal's residual bacteria may run deeper and longer than any daytime curve, because the repair fluid that would have neutralized it is absent. Accelerated dental decay that begins in the late 50s, the crowns, the root canals, the extractions that accumulate across the 60s, traces in part to prescriptions that suppressed the repair fluid. The teeth did not suddenly become vulnerable. The repair system that maintained them was pharmacologically compromised. Whether any of your medications should be adjusted, supplemented with saliva substitutes, or managed through modified oral hygiene protocols is a clinical conversation with your physician and your dentist. The physics teaches what each medication does to the salivary flow that maintains the enamel. The clinicians determine the appropriate response for your specific medication profile. One additional physics remains, the one that produces the sharp shooting pain from cold water or sweet food that arrived when the gum line receded. Why does the exposed root hurt? Gum recession exposes the root surface. The buccal plate, the thin layer of bone on the outer face of the tooth, is the thinnest bone in the jaw, sometimes less than half a millimeter thick. Aggressive brushing at the gum line, particularly with a hard bristled brush using horizontal strokes, abrades the gum tissue against this thin plate. The tissue recedes. The root surface, designed for the protected environment beneath the gum, appears in the mouth. Root cementum, softer than enamel, dissolves at pH 6.2, nearly a full unit above enamel's dissolution threshold. The root surface dissolves at a pH that normal saliva briefly reaches during routine eating. Material designed for the protected environment below the gum line, shielded from acid, shielded from thermal cycling, shielded from mechanical abrasion, is now exposed to the oral environment it was never engineered to withstand. The root surface dissolves at a pH the mouth routinely reaches during normal eating, a dissolution that enamel resists, but cementum cannot. Root caries, the decay that forms on exposed root surfaces in the 60-plus demographic where gum recession has progressed enough to expose the root, progresses faster than enamel caries because the softer material dissolves at a milder acid concentration and the dissolution threshold is closer to the resting pH of the mouth. Beneath the cementum lies dentin, permeated by microscopic tubules approximately 1 to 2 micrometers in diameter, filled with fluid that extends from the outer surface to the pulp where the nerve sits. Cold liquid, hot food, or sugar applied to the exposed root causes the fluid in the tubules to move. The movement deflects mechanoreceptors at the pulp end of the tubule, triggering an action potential that arrives at the brain as a sharp, shooting pain. Fluid movement in dentin tubules, rather than direct nerve stimulation, produces the characteristic pain of exposed dentin. Brenstrom described this hydrodynamic theory in the Journal of Dental Research. Sharp pain from cold water on an exposed root is fluid dynamics in microscopic tubes, moving a column of liquid by micrometers, deflecting a pressure sensor through the same mechanotransduction physics the ear uses to convert sound pressure into neural signals. The sensitivity is proportional to the number of open tubules on the exposed surface. More recession means more exposed tubules, which means more fluid columns responding to each thermal or osmotic stimulus, which means a stronger composite signal arriving at the pulp nerve, which means sharper pain from progressively milder stimuli as the recession advances. The pain is sharp because the fluid movement is rapid. Cold liquid produces a faster thermal contraction of the tubular fluid than warm liquid produces expansion, which is why cold triggers the pain more reliably than heat. The directionality of the fluid movement determines whether the mechanoreceptor fires. Outward flow depolarizes the sensor, inward flow hyperpolarizes it. Cold produces outward flow. The pain is directional, not just thermal. The year the dental problems accelerated mapped to the year the prescription arrived. The connection carried different weights. The week the salivary suppression reached a number I could attach to the flow rate my dentist had measured. Teeth that maintained themselves for 4 decades lost the repair fluid when the prescriptions arrived. The timeline is specific. Many viewers can identify the year the dental problems accelerated, and that year often coincides with the year a new medication was added. The correlation is not coincidental. The medication reduced the salivary flow rate. The reduced flow shifted the Stephan curve balance toward net dissolution, and the enamel surface that had maintained its mineral content for decades began losing mineral faster than the diminished saliva could replace it. The decay that followed was pharmacological, not dietary. The dissolution that saliva had been neutralizing every day now ran longer, recovered slower, and rebuilt less. The crystal was still dissolving after every meal. The crystal was no longer being rebuilt between them. 3 converging physics, structural fatigue, chemical dissolution, and a repair system, the prescriptions, delivered the tooth to the cycle where the bread was enough. The bread was the last cycle. The history was the cause.